In the last video, we just sketched the derivative of exponential functions and saw that our sketches suggested a really powerful relationship, that the derivative of an exponential function was just a multiple of the original exponential function. We're going to get a little bit closer to proving that right now. We're going to actually calculate, using the limit definition of the derivative of an exponential function, b to the x. So I've drawn a representative exponential function here. Now I had to make a choice to either draw exponential growth or exponential decay. I chose to draw exponential growth. All of the algebra that we're going to do works just as well for exponential decay. So I know if I'm taking the derivative, I would have a point, x, and then the y value would be b to the x. And I would have a nearby point, x plus h, and then the y value, I'm putting x plus h in that input position. So that puts it in the exponent. It's going to be b to the x plus h, so that the entire exponent is x plus h. There's my secant line, and I know that this is going to be the limit, as h goes to 0, of rise over run, b to the x plus h minus b to the x, just over h. Now, this is an indeterminate form. Top and bottom both go to 0. Clearly the 0 does, or the bottom does rather. If h were 0, this becomes b to the x minus b to the x. That's going to 0 as well. Okay. Now, I'm going to actually do a little bit of factoring in a moment, but it doesn't immediately look like I can. What I need to do first is just use the rules of exponents. Here, I'm adding x and h in the exponent position. Well, when do we add exponents? We add exponents when we're multiplying. So that's b to the x times b to the h. We're more used to using the rule to go from here to here. If I'm multiplying two powers of b, I know to just add those two exponents. But I can use the rule to break that apart into a product of two different powers of b. Now when I do that, I can now see that there's a b to the x in both terms on top. So I can factor that out. So I can say this is the limit as h goes to 0 of b to the x times b to the h minus 1 over h. When I factor out the b to the x here, there's a place holding 1 held there. All right. Now, if I look at this, I'm going to just rewrite this one more time. I'm going to actually completely separate that b to the x from the part of this expression that has h's in it. This is the product of b to the x times b to the h minus 1 over h. This factor here does not have any h's in it. This is what we call constant with respect to h. Okay. Remember, on my picture here, this was the point of tangency. I'm thinking of x, and therefore b to the x, as being fixed but unspecified numbers. This point isn't moving. It's this point that's moving closer to this point. This is representing a constant. I just haven't specified which constant it is. But if that's constant, I can use my constant multiple rule for limits. And I can factor out the b to the x and say this is b to the x times the limit as h goes to 0 of b to the h minus 1 over h. And that's because b to the x is constant with respect to h. There are no h's in it. Now this limit, we've still got an indeterminate form. The bottom's clearly going to 0. B to the 0 would be 1. 1 minus 1 is 0. Top and bottom are both going to 0. I don't see any techniques that we've had this semester that are going to help us evaluate that limit. I'm not going to be able to factor and cancel. I'm not going to be able to rationalize and cancel. I might try squeeze theorem, but I don't see any obvious candidates for what this is in between. Okay. So here's a place where we're going to admit that this limit goes above and beyond the skills that we have acquired so far this semester. We are going to need to rely on the mathematicians that have gone before, at least for a little while. Okay. But notice, if this limit exists and is a number, what I've got is a constant times b to the x, confirming our suspicion that the derivative of an exponential function is a multiple of that exponential function, that the derivative is proportional to the exponential function. Now, what we're going to do is we're going to rely on the mathematicians that have gone before to say two things. One, for any positive number b other than 1, this is in fact a number. So for any legitimate base for an exponential function, this limit does exist and is a finite number. So with that information, which we can't prove ourselves, but we can accept graciously from the mathematicians that have gone before, this does show that the derivative of an exponential function is a multiple of that exponential function. What I'm going to do is I'm going to tell you if b happens to be e. That's what we call the natural base. Okay. If b is e, I'm going to go ahead and tell you what this limit is. The limit as h goes to 0 of e to the h minus 1 over h happens to just be 1. Okay. That's very, very special, because that means that the derivative of e to the x, just replacing the b's with e's here, I'm going to get e to the x. This limit, when the base is e, is 1. It's just e to the x. E to the x, the derivative is not only proportional to the original function, but the constant of proportionality is 1. So that the derivative is equal to the function value. Okay. So what we've got then is that the derivative of e to the x is just e to the x. We've also got some partial information about other exponential functions. The derivative of an exponential function with a base that's different from e is going to be some multiple. I'm just going to call it k for now, where that's a constant. It's going to be a constant multiple of that exponential function. Now, I could just tell you what the limit is in all cases. We're actually going to see, once we've learned something called the chain rule, which is a few sections away, we're going to be able to figure out what this constant is by using the chain rule and this one piece of information where I had to tell you the result of one of these limits that we didn't have the tools to do on our own. Okay. So I'm going to leave you in suspense for now. I'm going to tell you that yes, it's true that the derivative of any exponential function is a constant multiple of that exponential function. What that constant is, we will be able to figure out ourselves in a few more sections. So the new thing that we're adding to our list of rules this section is that the derivative of e to the x is just e to the x.